So talking about collisions, perfectly inelastic collisions. Again, it doesn't in the AP exam. They may not necessarily say perfectly, but if you see the word inelastic, usually what that means is that you have two objects of different entity, separate objects with individual velocities that come together, and afterwards they're moving together as one unit. Okay, so an inelastic collision means there's no elasticity, there's no rebound, they stick together and then they stay together. So imagine a bullet being shot into a block of wood, right? The bullet gets stuck in the block of wood and then they're moving together. Or if you take the example I used earlier, let's say you take, how about this? Let's say you have a potato and you fire it with a potato gun into a can, right, or into a box. So here's your can, right, and you fire it. The can should clearly be bigger, but whatever. Let's just say it fits into the can. Okay, so the potato has a certain mass. The can has a certain mass. The potato has a certain initial velocity. Okay, so I'm saying v naught comma 1, meaning it's the initial velocity of object 1. And then afterwards, they are moving together. So you got the can with the potato inside of it. Okay. So here's the thing. If the can, or sorry, if the potato is fired and it hits the can, if it pushes on the can, okay, then the can will experience a change in momentum because it's experiencing a force, right? And so how does the momentum of the first object change as it is pushing on the second object? What do you think? What do you guys think? Sure, what? Decrease. By how much, relatively speaking? Let's take a look at this one graph again. I want you to think about this graph and the person kicking the ball with his foot. If the person kicks the ball with his foot with this much force, over this much time, how much force is being exerted on his foot? Seeing as how I didn't give you any numbers, it's going to be a relative description. Is there more force on his foot? The same amount of force on his foot? It's the same amount of force, because Newton's third law, right? For every action, there's an equal opposite reaction. So if at any moment there's this much force acting on the ball, that much force is acting on the foot in the other direction. And so that means that you should have an exactly identical force versus time graph on the foot in the other direction. So if the soccer ball gained 5 Newton seconds of momentum up, how much was the momentum change of the foot? 5 Newtons seconds down. It has to be the same. It has to be the same. So what Newton's third law essentially says is that momentum, because the force is always equal, that means the momentum change is always transferred, so to speak. It's conserved. If something has to gain 2 Newton seconds of momentum, it must have got it from somewhere because the equal amount of force is going to be applied onto the previous object in the other direction. So when you look at the law of conservation of energy, what it really is a restatement of Newton's third law. Law of conservation of energy, or sorry, not energy, momentum. I hope the cadence of which I'm speaking you can watch on YouTube at like 1/2 speed. Then you can kind of watch through these pretty quick because I'm writing. Okay, so law of conservation of momentum. In the absence of external forces, a system will conserve its momentum. Okay. What you consider to be the system is entirely arbitrary, and it shouldn't matter. Generally speaking, though, you want to choose a system where there's no forces acting from outside the system onto the system. Or else you have to take that into account so for example, if you have, let's say you have a bird, a falcon diving down to eat another bird or like catch another bird, okay? At that moment, gravity's acting on both of them the whole time. So the whole time, there's always a change in momentum downward of whatever their weights. That's always, occurring the whole time. So in order for them to maintain afloat, something must also constantly be pushing them up, whether it's from aerodynamic forces, they're flying, so on and so forth, they're beating their wings to throw air down, whatever it is, right? There must be something that would have to be taken into account. Makes the system pretty complicated, which is kind of why I used, an object just kind of trying to keep things just floating there, right? I'm not really taking gravity into account in this. Okay. So, how do we make these calculations? Let's take a look. So, by conservation of momentum, what it means is that if I'm looking at this system as a whole, both of them are contained within my system, the momentum that it starts with should equal to the momentum that it ends with. So the sum of the momentums, which initially only is the mass of the potato, times the velocity of the potato, the initial velocity of the potato, and that will equal to the mass of the potato in can times the velocity afterwards. And so from here you can figure out what the final velocity is if that's what you want, or whatever it is you're trying to calculate. Maybe there's a problem where you need to determine the mass of the can, and so you just need to measure the velocity afterwards and you work your way backwards, or whatever it is, right? The point is, by using conservation of momentum, it's one additional constraint or equation that you can use for determining information. All right. Any questions so far? Okay. Let's look at another example of collisions. So let's say we have a collision here where you have two balls. One's going this way, one's going this way, and they collide like right here. And then afterwards, they're stuck together and they're moving off to the side. And let's say this is 2 kilograms moving at 2 meters per second, and this is 3 kilograms moving at 5 meters per second. With this information, you should be able to determine the direction of motion of the inelastic collision. Okay, so here's how you do it. Let's do it in vector form. So if this is going purely in the I direction, this would be like a negative 5j. You guys remember your vector notation? Okay, so that you have this coordinate system, ij. It's like a collision. It's just me drawing a little collision. Or, I don't know, pow. Whack. Kablam. Or whatever. Try and figure out the final velocity as a vector. Do it in vector form. Vector form will make it a lot simpler instead of doing magnitude and whatever Tell you what, if you're kind of stuck, you can try this. Just think about what is the sum of the momentum in the x direction. What is the sum of the momentum in the y direction? Right? If you can do that, you know, then you're going to get your I term and your j term.
Is that a 3 or a 5?
This one is a 5. And that's a 3. 3 kilograms, 5 meters per second down, and 2 and 2. Just give it maybe 30 more seconds. All right, let's go ahead and just kind of work through this one. So the way you kind of want to solve these, especially if it's inelastic, pretty much just compare in the momentum before the collision and then the momentum after the collision in each direction, right? So the momentum in the x direction initially is your 2 kilograms times the 2 meters per second. Okay, that gives you 4 Newton seconds, right? And that needs to equal the momentum afterwards, which will be 5 kilograms times whatever the velocity is in the x. Right. So this should give you that the velocity in the x is 4/5 meters per second. And then you do the sum of the momentums in the y. This one is 3 kilograms times the negative 5 meters per second, which gives you the negative 15 Newton seconds. And that needs to equal 5 kilograms times the velocity in the y. And so that gives that your velocity in the y. Or sorry, this should be in the I direction, and then you have negative 3 meters per second in the j direction. So you get V final is equal to 4/5 I minus 3j meters per second. Question, some of you? Is it just hard to see? Cool. Questions? Yep. Jacob?
These types of problems, will we always write our answer in that format, or can we use coordinates?
Well, it wouldn't be coordinates. Okay, they're definitely not coordinates. it's either going to be vector form like this, or it will be magnitude plus angle. So you would do whatever Pythagorean theorem on this to find the magnitude, and then you'd have to do some trig to figure out the angle relative to, I don't know, the horizontal or something like that. Yeah. I think actually on Mastering Physics, they tend to ask for magnitude and direction. Okay. Lastly, with the only got like 2 minutes left, so I only set up the problem. Sometimes you'll also see explosions. Okay. So if a collision is 2 objects that are separate with separate velocities coming together, then explosion is 1 object that then afterwards becomes multiple objects, right? So let's just say, for example, you have like a potato. Okay. And sorry, I'm not zoomed. Okay. Okay. And this is just an example. You got your, 2 directions, right? I, J. But at this moment, we'll say it's at rest. Okay. And let's just say there's no, again, there's no gravity acting on it. There's no forces acting on it. Like it's, it's like in deep space. So, like space potato. Okay, space potato. So you have space potato, it's just sitting there. And then you got this 3 kilograms, and then it just explodes. Yeah.
If it's a uniform explosion, wouldn't the net momentum be 0?
It actually doesn't matter if it's uniform explosion or not. Any kind of explosion will still have, for the system, the net momentum is 0, which is actually really the main point. No matter how the pieces fly apart, let's say there's like a piece up here and a piece down here, and then like a piece kind of flying off in this direction. You can have different velocities. Say this is 2 meters per second. I'm just using whatever numbers. This is just an example, right? And we didn't have time to do the whole thing all the way through, but I'll just kind of give you some numbers, and then you guys can kind of check it yourself. What happens to the third piece, right? That is really kind of the primary point here, is that the sum of the momentums in the x is 0, and the sum of the momentums in the y is also 0, because it started at rest, right? At least at rest relative to our system's kind of reference frame, right? I'll just put the answer here, and then you can kind of try it yourselves later, that the velocity of this third piece is going to be negative 2I minus 2/3 j. All right? Oops. All right. That's it. We are out of time.